You're just looking at a monthly average in each band. So it gets rid of.
If during the start and also the end of the time, we recorded the event or we recorded the earthquake. So also the PSDL is also shown the influence because of the event.
I don't, well, the monthly plots these are means for per month. So things like high level earthquakes are kind of averaged out. You're just seeing changes in the mean through the month. The earthquakes, I don't understand why my cursor won't show, but if you look in the upper left panel, the earthquakes occur as low probability pink lines at the very top of that plot. What we're looking at in the monthly plots is just a variation of the mean. So all of those high level earthquakes are averaged out. I think, is that what you're getting at? What's the effect of the earthquake on these plots?
Yeah.
Yeah, you shouldn't see any earthquakes really in the seasonal monthly plots. Okay. All right. Moving forward, that was GSI.
Excuse me, Mr. McNamara. I
Yes.
have one question about why instability in the long period only are often occur in the horizontal component. Well, it is not happening on the vertical component. Is it the horizontal component more susceptible to environmental variation, Mister? Thank you.
Yeah.
Yes.
I think the
horizontal components are much more sensitive. If you think about, say, what's the vertical doing as it tilts, it just doesn't move as much as the horizontal components are moving. So you see that sensitivity only really in the horizontal components. The vertical component looks great here, but the horizontals will show that tilting noise due to the thermal and the atmospheric variations. That's very common. You'll see that in many stations. The only time you really can get horizontal components that look like this vertical component is when you're deep in a borehole, for example, 100 meters or more depth. I'm guessing again that this site is probably in a shallow vault and maybe not well insulated, possibly. So it sees a lot of thermal variation and pressure variation throughout the day. Okay.
Okay, thank you, Mister.
Thank you. Let's see. Okay, next station that we can look at, BKNI. That's again moving south. Again, this is we're looking at the BH channels. Again, it's an STS2 according to the IRIS metadata site. The thing to note about this, if you look at the PDF in the lower right, this one has quite high short period cultural noise. You can see at periods of about 0.5 seconds that noise that actually goes above the high noise model, which is fairly high. That will start to really impact your detection threshold for smaller magnitudes like magnitude 3 and 4 earthquakes. I've labeled an earthquake here on the PDF plot. There was a magnitude 6.7 on, what was it, mid-April of 2021. And so you can see the PSD for that across the top. That's some of the highest powers in the PDF. That 6.7 was about just a few hundred kilometers from the site. So it's well recorded. And I think I showed that in the previous one as well. Did I? No, I guess I didn't. Sorry. Going forward. So you can see there's an earthquake. It goes across the whole top of it. I'll show an example, a little better example here coming up where we can look at it as a function of detection. But the thing that I wanted to note about this particular station is that the high frequency noise is pretty high. And so I'm guessing again that this station is located near a city possibly. I don't know if that's true. Does anybody know about the location of this? Is it located near a popular, highly populated area at all, or near a road possibly? Maybe no one's been there. I just thought I would ask.
Well, it's not real high population, but average for the general for the country.
Okay.
Road, some roads, not heavily traveled. It's very topographically, it's very
Steep.
hilly,
right?
steep, very steep. Yeah.
So it could be a topographic effect then. That's a possibility as well.
Yeah.
Or site resonance if it's in soils, possibly that can happen if it's in soft soils. If it's in a hilly area in a basin, you might get resonances in that basin.
It would be in volcanic soil.
Okay, that's a possibility then, where you can get resonances in the soil itself. So that's something that would be interesting to look into, because that could have an effect on seismic hazard, for example. And when you get soft soil resonances, it can really affect structures. So that's something interesting to look into possibly. Okay, so
Daniel,
yes.
can we estimate the magnitude from the PSG?
Not really. Possibly you could. I just looked this up. I just looked at the time of it and saw that there was a magnitude 6.7 nearby at that exact time. So you possibly could, but most algorithms are going to work off the time domain, off the time series. Okay. Okay, moving forward again, you see here are the here's some diurnal plots again where I've binned everything by hour of the day. Again, you can see this very strong diurnal variation in the long period horizontals. No variation at all in the vertical. If you look at the bottom right plot, that thick blue band, that means that the vertical component long period is just sitting there fairly stable, but the horizontals are moving around quite a bit. So again, like the question that you asked earlier, the tilting doesn't really affect the vertical component, mostly just the horizontal. Okay. So again, very, very common in most of your stations. And also that short period has quite a bit of variation too. It's high most of the day, but then for a few hours in the late night, you can see that the noise levels at the short periods drop down for just a few hours during the latest part of the night, earliest part of the morning. Okay. Here, let's look at, I wanted to show some examples. Here's some, I looked into the 6.7 a little bit more. Here's the, if you look at this map, you can see the station GSI is right here on this island. We showed an example of that. And then down to the southeast is BKNY and I. That was the last example we showed. And then these orange circles to the west are a cluster of earthquakes. There's a magnitude 6.7 and a lot of aftershocks. And I'll show a couple examples, the 6.7 and the 4.2 compared to the median noise levels at station GSI and BKNY, just to show you how well these are recorded or not well in the case of the 4.2. That's kind of hard to detect. Okay. So moving forward, here's, this is kind of a busy plot, but the plot to the right shows in the orange lines show the PSDs for those two earthquakes. There's a magnitude 6.7 at 170 kilometers from station GSI. And then the other orange line is a magnitude 4.2 that I showed in that same cluster And then the blue line is the median noise level for BKNI, and then the green line is the median noise level for GSI. So you can see that that magnitude 4.2 is sort of barely above the noise levels of the BKNY. Oh, I'm sorry, I switched to frequency here too instead of period. I don't know why I did that, but I prefer to think in terms of frequency sometimes when I'm dealing with Brune spectra and earthquakes. So everything's flipped here for this particular plot. Sorry to make you do an inverse in your head here, but these are all in frequency instead of period. So they're all a little bit backwards. But the other thing I wanted to show is these red lines with the circles. Those are Brune spectra amplitudes for magnitude 6, 5, 4, 3, and 2 at 3 different distances, 0.5 degrees, 1, and 2 degrees. And so I just wanted to show that's the amplitude at the source corner frequency according to a Brune spectra. If anyone's studied Brune spectra, you know what I mean. It's an amplitude modeling code written in the 1970s by Brune. It's for S waves. I've modified this to work for P waves by just making it a little bit smaller according to another reference by Anderson. So what these red circles show again is the amplitude of a certain magnitude at a given distance at the source corner frequency. And so what you can see is the magnitude 6 lines up pretty closely with the 6.7 recording. Not quite, but pretty good for a model. And so you can see we're pretty close. And then the magnitude 4 Brune spectrum model lines up pretty well with the orange line, which is the 4.2 recorded earthquake. So you can see the model's not too far off. And so we can use that to sort of look at how well these particular stations would detect a certain size earthquake. So what you can see, for example, let's look at the blue line. That's the median of BKNY. So what you can see with that is that BKNY probably could not detect a magnitude 4 earthquake at a distance of 1 degree, okay? And certainly at 2 degrees. But at 0.5 degrees, you can see that magnitude 4 is above that blue line, suggesting that it would barely be detected. Okay, if you go down to the right a little bit, the magnitude 3 circles, those are all well below station BKNY and BKNI, and also below the GSI green line. So this would suggest that from the Brune source modeling that both of these stations could probably not detect a magnitude 3 greater than a 0.5 degrees. Which, that's maybe you don't care about magnitude 3s, but if you're looking at B values and trying to model smaller earthquakes, looking at operational earthquake forecasting, where you're again computing magnitude frequency distributions for smaller events, you want to be able to detect these little events as well. And so I just wanted to show that with these stations, the high frequency or short period noise levels from about 1 to 10 hertz are pretty high. So you really are not able to detect these smaller earthquakes very well. Magnitude 6, no problem. Magnitude 5, no problem. But when you get down to 4, 3, that's when you start to get towards the detection threshold of these particular stations.
Daniel,
I'm sorry. Yeah, go ahead. It's a very busy plot. I'm sorry.
Is it related to the magnitude saturation?
I'm sorry, I missed that.
Is it related with the magnitude saturation?
Magnitude saturation?
Yeah.
I'm not sure what you're referring to there. Is it?
He's confusing what you're showing of lack of detectability and so on with the phenomenon of magnitude saturation, which is something completely different. Maybe
Oh,
you can explain this, completely unrelated.
these are MWs, so there should be no magnitude saturation in this. The red lines are Brune models, so they're not real earthquakes. They're just it's an MW calculation, and then this is the amplitude of the P wave is what I'm showing here. So there should be no saturation, and again, the orange lines are recorded earthquakes. So yeah, there's no saturation whatsoever. Okay, no clipping, no nothing. So. Again, the magnitude 6 and 5 are well recorded, but the others are questionable. Does that make sense?
Yeah. Okay. Thank
Okay.
you.
Okay. So I just wanted to show you this for a kind of a rough range of detectability. So as we look at these moving forward, you'll be able to have a sense of what a good looking station is. You can see again, the green line, that's the median for GSI is well below. Oh, I forgot to mention again, these black lines are the high and the low noise model. So when you're up around the high noise model for a median noise level, then that's really going to affect your detection capability. You really won't be able to detect magnitude 4s and smaller very well. Okay. But below the low noise model, then you can probably detect 4s, and depending on how low you get, if you're down at the low noise model, then you can probably detect magnitude 2s. But I don't know that there are many stations where that's doable here. Okay. Okay, that's a very busy plot. I hope it's not too confusing, but I'll send this to you and you can have a look at it in the future if you'd like. Okay, moving south again to the next station, PMBI, the next station to the south. Again, this station, has an STS2, we're again only looking at the broadband channels, BH, E, N, and Z. And again, if you look at the lower right PDF plot, this has very high short period cultural noise. Just to confuse you again, I've gone back to period instead of frequencies. So do that inversion in your head again. The lower right plot shows the PDF in period. And so to the left of that plot is the short period high frequency band. And if you remember that previous plot on detectability, that high level of noise would cause you problems all the way up to magnitude 4.5, maybe almost 5. So that's a pretty high noise level, and really would affect your ability to detect smaller magnitude earthquakes. Again, the higher level light pink PSDs at the top of that plot, that's that magnitude 6.7 again that you can see easily recorded. That's very high power. Okay, moving the next one. Again, we'll look at these diurnal plots. Again, the same sort of pattern. You get that very unstable long period behavior in the horizontal components. You can see it never really settles down. It's all smeared out. The PSDs are very broad and smeared, suggesting that it's constantly moving. And again, probably a relatively shallow vault in soft soils that's moving as it heats and cools, or due to atmospheric pressure changes. And again, to the left of these PDF plots, you see that very high short period cultural noise in all three components, the horizontals and the vertical. And again, this is probably due to being located close to a road or close to a small village or a city. I'm not sure. I didn't really zoom in to have a look, but it's fairly high cultural noise compared to many of your other stations. That might be one of the highest noise levels that I've seen at the short periods anyway. The other thing too to note is that the vertical component here even has a fair bit of diurnal variation. So you can see even the vertical is moving a little bit more. So that suggests that it's really going through a lot of tilt. If you can see it on the vertical, it's moving a lot. So this would be a good candidate for trying to build a better vault that's maybe deeper into the ground on bedrock, or a post hole that's a few meters down into the ground, and well insulated. Also, it's good to pack that vault with insulation and to minimize the air movements and the thermal variations. Okay. Any questions at all on this station? It's a bit repetitive. I'm showing a lot of the same kind
Dennis,
of features.
excuse
Yes.
me. Yeah, I'm interested in this feature. So you say that the station has high cultural noise, and you also say that maybe the recommendation is to make a good vault in the bedrock and also the insulation. So my question is about how to make a better insulation in our seismometer.
Well, generally what we do at the USGS is when you have a vault, there's many things you can do. If you have a concrete pad in the vault, you want to isolate that from the walls of the vault. So if the walls are moving, then hopefully the concrete pad inside won't move as much. So you don't want to pour the concrete all the way to the edges, because then that'll cause the whole thing to tilt. So that's one way to do it. The other thing to do is when you do once you put the sensor in the vault, it's best to pack in fiberglass insulation or build a box of styrofoam insulation over the sensor. Anything you can do to pack that in to minimize pressure changes or air currents, anything like that. These are very sensitive. These STS2, Streckheisen STS2 sensors are very, very sensitive. So again, digging deeper into the ground, getting on bedrock, isolating it from the walls of the vault, and insulating will go a long way to improve the long period noise. The cultural noise, the short period, that's more difficult. That you actually have to locate away from a road or away from machinery. Sometimes you just cannot improve the cultural noise with a better vault. You just have to pick a new location if you really want to improve it. And you often don't get that opportunity. You have to put a station where you have the available land or location. So in this case, you might not be able to improve the cultural noise. One way you could do it, which is very expensive, is to drill a deep borehole and just get deep into the earth. The USGS and IRIS operate many stations in the global seismograph network, and many of the stations in Indonesia that I showed in the last lecture have a deep borehole that can lower the noise levels at both the short period and the long period end. Okay, that's the long answer to your question. Does that cover?
Yes, thank you.
Yes, thank you. Okay, moving even more south, here's station MNAI. This one's very interesting. It's on the southern end, and so it's right there close to the Pacific Ocean. You can see, I guess that would be the Indian Ocean, or both, isn't it? It's open, it's close to the open ocean, and what you can see there is the microseism peak is just very high and very wide. And so that's pretty unique. That's just from being so close to the open ocean. There's not much you can do there. Again, this station has an STS2, and it has very high microseism noise levels. It has fairly high short period cultural noise, not as high as the previous example, but still very high, near the high noise model at 1 hertz, but a little bit below the high noise model at the shorter periods. So it's looking a little bit better than the previous example. The microseism, again, there's not much you can do there. You're near the ocean. There's just it's going to be high in a place like that, in a station located near the ocean. Okay. And usually when you're near the ocean, the microseismic peak gets broader because you have many different frequency waves in the water and that are coupling energy into the earth instead of just the standard microseism peaks that we're more used to seeing. Okay. And again, this station has very high long period noise levels. If you look at the PDF plots on the left, they're fairly stable. You can see the green colors indicate that it stays at a relatively consistent noise level, unlike the others where it was smeared and moving around a lot. This is fairly stable. It's just also high noise levels. It crosses up across the high noise model. Okay. So there's a little bit of diurnal variation, not too much, quite a bit of diurnal variation in the short periods, suggesting again that the cultural noise will vary from night to day. But again, this is not a bad station compared to a couple of the others we looked at that had the short period noise well above the high noise model. And again, there's just not much you can do in a lot of these cases. This again, though, would probably benefit from a vault that is well insulated and maybe dug a little bit deeper down to bedrock. And I know I'm being quite repetitive, but the seems like a pretty standard, pretty common theme here. It would be interesting to see what your stations look like. I was kind of looking around on the internet for photographs, but I couldn't really find much. It'd be great to see what they look like, and I could probably provide more input on construction details if needed. Okay. How are we doing on time? It's almost 1 hour, isn't it? Okay. Moving forward, the next station down, moving south, BBJI. This one looks really good, I have to say. Again, it's an STS2. We're looking at the BH channels. It's interesting how much lower the microseism peak is here. I don't quite understand why it would be so low, given that it's so close to the ocean, but it is. And it also has very low long period energy on the vertical component here, and relatively low short period cultural noise. You can see on the left side of that PDF plot, the noise levels are quite low. So you can imagine, compared to the previous two examples where the median noise levels were at the high noise model and above, this one's quite a bit lower. It's actually closer to the low noise model at the shortest periods. So this looks like a really good station. Moving forward, take a look at these horizontals too. Very good, very stable. There's hardly any diurnal variation in the long period horizontals in this particular station. So whatever's going on at this station, it's really good. Does anybody know, is this station sitting on bedrock, or is it in a post hole or borehole, anything like that? Because this station looks really good.
Yeah, it's surprising. I would have thought like you.
Halo, Mas Melki. Tahu nggak stasiun ini, Mas Melki?
Yes. Ya, Pak.
Tahu stasiun ini nggak? Posisinya di mana gitu?
Oh ya, saya cek dulu, Pak.
Bedrock atau enggak gitu?
Just looking for any indication on the IRIS webpage, if it was a borehole or if it's deep. Doesn't really say. But this is good. It looks very good at long periods.
The station is in Pumpulang, Western Java, Mr. Supri.
Bedrock, Pak. Bedrock.
Di mana ya? Palembang ya?
Pumpulang,
Pak, Jawa Barat, Pak. Jawa Barat.
Garut.
Garut, Pak.
What is your elevation?
Ini Pak Taufik yang survei, Pak, dulu. waktu nyari lokasi.
Di puncak gunung ya?
Katanya di batu Pak, di atas batu, bedrock mungkin Pak.
Iya,
Kalau
iya.
dari geologi termasuk batuan tua juga sih Pak, tersier.
Oke.
Anybody
Tahu
know?
elevasinya nggak?
Gimana Pak?
Elevasinya berapa gitu?
Elevasi.
Well, whatever construction technique you have at this station, it's very good. I'm guessing it's probably still a shallow vault, but possibly sitting directly on bedrock, or it's deep. It's deeply buried and well insulated, something like that. Because the horizontal, long period horizontal components look really good. Yeah, and looking at these diurnal plots to the right, there's no variation hardly at all. It's very stable, even at the short periods. So that's there's something going on here. It's very good.
Iya.
Excuse me, Mr. Daniel.
Yes.
I want to ask about the horizontal component and vertical component for this slide and the previous slide. Why is it so different from the picture?
The vertical and the horizontal?
Yeah. The spectrogram for horizontal and vertical component in this slide is very stable, but the previous slide, the difference between vertical and horizontal component.
Yes. Well, in many of these examples like this, this is PMBI. As I pointed out, you can see the horizontal components are very noisy. They never stabilize. You see these smeared purple and pink colors. That's because it's moving around quite a bit, and you can see a strong diurnal variation. And as we suggested, this is probably a shallow vault in deep soils, possibly soft soils. But then as you go, if we go back to this one is very stable. The long periods, you can see those sort of light greenish to aqua colors, blue colors. That's suggesting that the long periods are settling down and staying fairly consistent, not moving around so much. So there's probably very much less thermal variation throughout the day, much less atmospheric pressure changes that the sensor is detecting. So I'm guessing here that this site, as opposed to the other one, this site is probably sitting on bedrock, or it's in a deeper hole and isolated from the soils, and maybe better insulated so that it's not experiencing thermal variations. It would be really interesting to look at photographs or get some details on the construction of these different sites so we can compare and see this particular site, BBJI. Whatever you've done here is probably worth looking into and emulating for other stations, because this looks very good. Okay.
Okay, thank you.
Moving forward again, one more. Let's see. Now we're heading east. This is station SMRI. You can see here on the map on the upper right. Again, it's the BH channels are an STS2 from Streckheisen. Excuse me, I'm yawning. The PDF plot in the lower right shows relatively high short period cultural noise compared to the previous example. This is probably in a more populated area, Central Java, I'm guessing. I don't know. I've never been to Indonesia, so I don't know, but I'm guessing it's a little more populated, so you're getting higher levels of cultural noise here. Also seeing a little bit of more noise on the long period compared to the previous example. What was that station? BBJI, that's the very good station. So this one is SMRI. If we look here, again at these diurnal plots, the daily variations, again, you can see pretty strong variations throughout the daytime for the long period. This looks a little more like some of the others. And you also have fairly strong daily diurnal variation in the short periods, and relatively high overall noise levels for the short periods. So again, pretty consistent with many of the other stations. If you look at the BHN component PDF, there's a funny looking PSD that goes along the bottom of the graph. That's probably a dropout, but it's only, looks like it's only in 1 hour. So for a 2-year period, you have a data gap in only 1 hour. So that's really good. That's very good telemetry and what's the word I want? Oh man, it's late. My brain isn't working. That's not many gaps. I'll just say that. That's very consistent data. Okay.
Daniel,
Yes.
can we make conclusion that the very sensitive sensor is not good?
It's good for recording small magnitude earthquakes. I do think strong motion is very good for you as well to record large earthquakes on scale. But I also think having a broadband weak motion sensor is important for recording smaller magnitude earthquakes, which are important for doing magnitude frequency distributions for operational earthquake forecasting, and also important for aftershock studies for identifying the active faults, locating aftershocks, things like that. So my personal opinion is that you want both. Every station should have a strong motion and a weak motion sensor. Does that answer your question? That would be my opinion.
Okay,
But
thank
it's also expensive to operate multiple sensors. But I think in most of these stations, I see that you have strong motion and weak motion operating, it seems.
Thank you.
Thank you. Okay, what else do we have here? Let's go.
Excuse
And
me,
moving.
Mr.
Yes.
I'm still a little confused that the 0.1 to 1 hertz, 1 hertz in macroseism, it is caused by macroseism or might be mixed with a cultural noise, Mr.
That's a good question. If you look at the diurnal plots, usually if it's cultural noise, it'll have a variation throughout the day. Again, where activities of people are causing higher noise levels. So if you look at the 1 second period, say in the upper right panel, the BHE diurnal plot, at 1 hertz, there's just a little bit of variation. You can see a hint of light blue at the end of the day and green in the earlier part of the day. So there's a slight bit of variation indicating that it's at 1 second period. It's probably more related to cultural noise. But you're right, in this particular one, the microseism and the cultural noise kind of blend together. But you can see it's a bit of a low at 1 second and lower periods until it goes up to that peak again. So that low point is probably the separation between the culture and the microseism noise. Okay, but you're right, they start to blend together when the microseism is so high.
Okay, Mr. Can this problem also solve by borehole installation, Mr.?
I'm not sure I understood your question. Can you say that again?
Um, can this problem about cultural noise also be solved by poor hole installation?
Yes, well, usually it's just based on proximity to the noise source. And there's not much you can do to, if you're close to a road or you're close to buildings, or even trees, actually. Trees cause noise at the higher frequencies or shorter periods. So there's not much you can do except dig a deep hole. Not even like to bedrock, but hundreds of meters into a borehole is what you need to do to get away from the cultural noise. But that gets to be very expensive and not always doable. Okay. Okay.
Thank you
Yes.
very much.
Thank you. Okay, moving forward again. The next station, UGM. We looked at, this one is again very similar. Let's see. Now this has lower short period cultural noise. So this station is really good. It must be located away from a city or away from a road. It has nice low cultural noise levels. Microseism is quite high, as you would expect near the ocean. But then at long periods, you also see quite a low level, at least on the vertical component. And then you can see I've labeled gapping. You get these very low levels when there are gaps in the data and it's filled with a zero. You take an FFT of that step and you get a PSD that comes in at a very low level like that. It's not real. It's not ambient earth noise. It's a gap in the data, most likely. Okay. So moving to the next, this is the diurnal variations plot for that station, UGM. You can see there's quite a bit of variation at the long periods and the horizontals, but the cultural noise short period band is very stable, hardly any variation throughout the day, just a tiny bit, but not much at all. So this station is probably more remote, I'm guessing. It's not located near roads or in a city. So this is a very good station at short periods that would help detect smaller magnitude earthquakes like the magnitude 3s and 4s that we looked at in that example. Okay. So again, this is a nice station. The horizontals are the long period horizontals are a bit noisy. They can be quite low, but they also move around a fair bit and have a fair amount of diurnal variation throughout the day. Okay. So this again is quite a nice station.
Daniel,
Yes.
what is actually the source of the long period noise? Noise 100 seconds. 100 seconds, yeah. What is
The
the
100
source? The main
the
source?
source, it's probably the thermal variations throughout the day. As I've shown, it's you get these strong variations throughout the day. So it's probably heating and cooling that causes tilt of the vault or the building. If it's in a building, you'll get pressure variations within the building. Are these generally in like a shed or a small house, or are they a little vault buried in the ground? Do you know?
Yeah, okay.
So if it's in a house, if it's in like a small house type shed, we would call it, then you could have the whole thing moving, or you could have air currents or pressure variations within the building causing this long period noise at 100 seconds. Okay. The next station, JAGI, as we get down towards the southern end here. Again, this is shown a couple features in this to look at. There's a magnitude 6 at 181 kilometers. You can see I've put an arrow on that particular PSD for the magnitude 6, so that's well recorded, no problem. There's some funny looking features in the PSDs in the upper right of the PDF panel that I've labeled STS2 recenters. When the STS2 moves a little bit, it'll recenter itself. And so you can see that sort of scalloping, peaky looking PSD on the light pink in the upper right of that panel. That's what a typical STS2 recenter might look like. So you're getting a little bit of recentering going on in this at this station, which probably means again that you're having some long period noise issues. On the short period, the noise levels look fairly good here. They're well below the low or the high noise model, so that looks fairly good. Let's move forward again. So yep, if you look again, the long period horizontals are quite noisy. And so that's probably related to the STS2 recenter that you can see. So again, if the vault is moving so much, or the pad is moving so much that the STS2 is going out of center, it will try to recenter itself automatically. And so you can see that as these scalped looking PSDs on the vertical component. I'm not sure why it's not on the horizontal, but it shows up mostly on the vertical actually. And again, you can see on the horizontals, the higher level PSDs are probably related to that magnitude 6 that I pointed out in the previous slide. Again, at this station, you're seeing very strong diurnal signal in the long periods, and just a little bit at the short periods, not so much. This is a fairly good station at the short periods. Again, probably located relatively far from a road or from a city or active places where humans are active and going about their business. Okay. Again, very similar. Most of the stations have this long period tilting issue. Okay, moving on. Next station. This is a really good looking station, PLAI. The short period cultural noise is very low. The microseism is relatively low, and the vertical long period is very low. Again, the horizontal long periods are not that great. There's a lot of diurnal variation. And again, they're moving around quite a bit. As I've mentioned in all of these examples, it's probably related to tilting. And again, if you look down at that BHZ panel, the lower left panel, you can see that funny scalloping looking PSD at the very top. That's again an STS2 recentering itself, probably because the sensor is moving around a lot due to tilt of the pad that it's sitting on. Okay, I'm not sure I labeled that. I forgot to label that in this one, but that's the same kind of effect that we saw here at JAGI, that STS2 recenter that you can see in the upper right of the PDF plot is the same thing occurring here. So that's suggesting that you're getting a lot of tilt of the pad if the STS2 is recentering itself. Okay. But again, the short period noise levels of this station are quite good. And yeah, the station looks good, looks very good at the short periods. Okay, moving on to station MMRI. This one has quite a bit higher noise at the short period. You can see it's getting up close to the high noise model in that PDF plot. So this station is probably located again closer to cultural noise sources like roads and buildings and machinery. Microseism in the mid-band is relatively low. It's closer to the low noise model, which is surprising to me considering that it's so close to the ocean, but maybe on the north side it's not as noisy, but it looks pretty good.
Is it
Okay.
possible something wrong?
No, I don't think so. I think it's just, it looks pretty normal. Just a little lower than I would expect. I don't think there's a problem with it. Let's go to the next one. Here again, very typical. You can see fairly unstable long periods. Again, the same sort of feature that are a source that we've discussed in nearly every sensor, every station. A lot of diurnal variation of the long periods and the short periods. There's quite a lot of quite high noise levels at the short periods due to cultural noise. And so again, this is a fairly typical looking station that is okay, but probably could be improved with a little better vault construction or possibly a post hole type construction. If you remember the examples I showed from the GSN last week, the post hole sensors looked almost as good as the boreholes. So you don't need to go too very deep to get considerable improvement in the long periods and short periods. Okay. And let's see, next station, SO. Yes, someone have a question?
Okay. Is it possible to minimize the noise using filter technique, or maybe we must relocate the sensor with high noise to the, as you mentioned before, to the deep borehole or post hole, or maybe we improve the installation?
Improving the installation is the best way to do it. I think you started the question by asking about a filter. Can you do filter techniques?
Yes.
That's pretty hard to do without removing signal as well. I've never really seen that done effectively, but it is something to consider as a research topic. I've just never seen anybody do it effectively. Okay.
Okay, thank you.
You're welcome. Thank you. Okay, back to this station, SOEI. This one is fairly typical. It has pretty high noise, unstable long period, even on the verticals. So this one has probably particularly noisy, particularly noisy at the long period, even visible on the vertical. So this station's probably moving around quite a bit. Again, the pad tilting and again, could probably be improved with some insulation and slightly deeper vaulting. Okay. That's SOEI. I kind of forgot where that is. Okay, so that's over in Timor. That's far to the east. Okay, I believe the next stations we'll look at are moving up to the north. Okay, so there's SOEI. Again, strong diurnal variations at short and long periods. Even in the vertical, that's kind of surprising. You don't see that very often. I believe this is only second or third station where you see that the vertical component in the long period is also not very stable. So this one is probably could be improved with a better vault installation. Okay, this station is BKB, moving to the north. This one has very high short period cultural noise. It's up there along the high noise model for the most part. Has very low microseism, which is interesting. However, it has this really interesting feature that I've labeled local water waves. I've seen this at many stations throughout the world, usually an island station where there's a lagoon or some smaller body of water. You can see just to the east of this station, there's that narrower bit of water between the Sulawesi, between the two islands. And so that there's probably some resonances going on in the water there that's causing this really high noise level that I'm calling local water waves. That's at a period that could affect your detection capability for smaller magnitude earthquakes in the magnitude 3 and 4 range. If you remember that example I showed earlier. And then the microseism is really fascinating. You have multiple peaks from maybe 4 or 5 seconds out to almost 20 seconds period. And that suggests a really complicated microseisms, not just a single source, but multiple sources from many different depths in the ocean. But again, there's not much you can do to get away from that. The ocean is always generating this energy. And if you're going to be near the ocean, you just have to deal with it, basically. Okay, moving forward. Again, here are the diurnal plots. Again, you see this very strong daily diurnal signal in the upper right plot. The long periods are high during the day and lower at night. Almost 40 to 50 dB variation in the noise level. That's pretty high. That's a big range. So again, that could be vaulting, same as all of the other examples that we've shown. And then the short period noise, again, is also quite high and shows a fair amount of variation throughout the day due to proximity to cultural noise sources. Okay. And here's one I just wanted to show. Here's a bin by month for this station. I didn't have multiple years to be able to work with, but you can see a fair amount. I wanted to look into what this local water wave behavior is like. And what you can see is there's a fair amount of variation from month to month. It's probably related to storms out, maybe cyclones, something like that, or just general storms during the winter. It looks like the April, May, June are the lower levels. August, September are fairly high in that 1 second period. So you can see a fairly strong month-to-month seasonal variation of that noise level that I'm labeling local water waves. Okay. Maybe if you talk to local surfers, they'd know all about that, I'm guessing, because this is probably water waves coupling energy into the solid earth. Okay. And again, there's not much you can do to get away from that unless you put your station farther away from the coast. It's fairly short period, so it would attenuate away fairly quickly. Probably if you were 50 to 100 kilometers from the coast, you wouldn't see that at all. In fact, I think in many of the other stations that we've looked at, we haven't seen that particular high noise level at 1 to 2 seconds period, like you see here, where I've labeled it local water waves. Okay. Let's see, the next station, TOLI. This one is a very good station. The noise levels across the whole band are fairly low. Low short period cultural noise, very low microseism, which suggests it's far away from the microseism sources that are probably out in the deep ocean. And then it also has fairly low long period, at least on the vertical component. Okay. This one is a very good station overall, except for, again, this issue with the horizontal long period components being fairly unstable. But I don't want to make you feel like these stations are terrible. I'm not trying to say that. I don't mean to be so critical. This is a very common thing with STS2 sensors. They're very sensitive, and you have to put a lot of insulation and a good amount of effort into making a nice, stable volt. Yes.
The sensor located near the ocean,
Mm-hmm.
but why the noise microseismic is too low?
That's a good question. It must be that the sources of the microseism are out in the deep ocean, out in the Indian or Pacific Ocean. The microseism sources are far away. Here in the shorter periods, at 1 second period, that's probably more local wave energy. But the at 5 to 10 and 20 seconds, that the noise sources there are far away in the deep ocean of the Pacific and in Indian Ocean. There's nothing nearby, probably. Okay. And
This was
again,
Dan, this was an important station for recording the September 28, 2018 Palu earthquake. It's the
Okay.
nearest, one of the nearest stations. It gave good data.
Okay, great. And I assume there's a strong motion channel there as well. According to the IRIS website, yes, there are strong motion channels as well. So you probably recorded it on scale.
Right.
With those. Okay. Again, the short period noise levels look very good here, and but the typical long period problem persists. And we'll just keep moving through the network. This one is not as good. This is LUWI. Again, it has a STS2 sensor and a strong motion. The short period noise levels are quite high here, suggesting it's near cultural noise sources like a city or a road. The microseism again is fairly low, but the long periods are also quite noisy, even in the vertical. You see some relatively high noise levels. The horizontals, again, typical unstable behavior where they really never settle out. They're moving, tilting probably fairly consistently throughout the day. Again, very strong diurnal variations in both the long period and the short period, of several tens of decibels, which is quite a bit of noise variation throughout the day. Okay, what station? This is LUWI. I want to see that map again. Okay, there it is. And then moving to the next station, SANI. This looks very similar. Fairly good short period noise levels, low microseism and low long period noise. But again, this typical long period unstable behavior. Everyone's probably tired of me saying the same thing, but it's very typical behavior and is an issue that you might want to consider dealing with. Let's move on. You've seen this. This one is TNTI. This has some STS2 recenter problems going on that you can see in the upper right of that PDF plot. Again, that scalloped, that multiple peaked PSD, that's what an STS2 recenter looks like when you take a PSD of it. The cultural noise is relatively high, but again, the microseism and the long periods look really good, at least on the vertical component, which is again surprising to me how quiet the microseism is in these islands compared to the stations down by Jakarta and Timor and places like that. Okay. This one is very interesting. The horizontals are very stable. The noise levels in the long periods are quite high, but they're stable. They're not moving as much as we've seen. You see how the long period probabilities kind of settle into that dark and light blue colors. That suggests that it's fairly stable, but again, relatively high. So I'm not sure what's going on here. There's a little bit of diurnal variation, but not as much as you've seen in other stations. And also some diurnal daily variation in the short periods. Again, that's due to proximity to a road. Most likely that energy up around 10 hertz or 0.1 second period is related to automobile traffic, is usually what it is. Okay. And okay, here's a station that gets very, very high noise levels from the microseism all the way to the short periods. So you can see from about 0.1 seconds all the way to about 3 or 4 seconds period. It's very high noise levels up around the high noise model. This station is on a very small island from what I can tell. So that's not surprising. You've got microseism sources, you have local water waves, you have all kinds of energy from the oceans coupling energy into the ground and causing noise on the seismic station. Okay. And again, even the long period vertical is not very quiet. It's moving around quite a bit. So when the long period vertical is not stable, that suggests that your vaulting needs work. Again, dig down to bedrock, insulate, isolate the pad. Some of those are fairly typical things you can do to improve the recording noise levels at the long periods. Okay. And then, okay, here's the seasonal view for that station. Just wanted to look at, I was so interested in this 1 second noise, kind of like the question that was asked earlier. I wanted to know what that was related to. And so in this plot, this is bin by month. The previous one was hour that you've seen many examples of. And in a few cases, I'm binning them by month, as mentioned. And so you can see a lot of month to month variation. It's January, February, March. Those are the letters. The first letter of each month is what's shown at the bottom of each of these plots. And you can see in the month of May, the seasonal microseism really picks up and gets strong. But then it's very low, and it looks like it's very low in April. So there's a lot of month-to-month variability that again probably has to do with storms out in the ocean and causing wave heights to increase in the ocean. Okay. And then not much variation from month to month in the seasonal, but a little bit in the long periods too. You can see that. So there's some seasonal variation at 100 seconds period from month to month, which is pretty interesting as well. Okay, and this is one of our last stations. I think there's 2 more left. FAKI, which is on the larger island there. This is a very good station. The microseism is complicated. It has that local water wave peak that we've seen in many cases, but also a very low microseism suggesting a faraway source out in the big ocean, and very low short period cultural noise suggesting that this is in a fairly remote location, and also low long period noise. This sensor is also an STS2, so very typical for an STS2. But again, as we look at these horizontal components, you see a lot of variation in the long period, very unstable, very strong diurnal variations, suggesting again that there's a lot of thermal and atmospheric pressure variation throughout the day that's affecting the long period channels on this sensor. Okay. And then the last station that I was able to process is GENI. This is on the North Shore of New Guinea. And it has fairly high short period cultural noise. So this is probably fairly near, close to a city or some roads. But the rest, the microseism is fairly standard for a station in this location, and has very low long period noise. Here's the final diurnal plot for the evening, for the morning. Again, you can see the horizontal long periods are very unstable and strong diurnal variation and quite high noise levels in the short periods up near the high noise model. Again, these could probably be improved with better vaults. Okay, and so after all of that, basically just have one recommendation that I've repeated many, many times. You have quite high noise levels on the horizontal long period components and also a lot of short period cultural noise. And a major consideration might be to consider these post hole type installations. If that's not a possibility, at least going back to the vaults that you have and trying to insulate them would be the very first step, I would say, to do, that you could look into. Okay. And that is my last slide. There's a lot of detail and a lot of data that we looked at. It's really hard to focus in on too much, but if anybody has any more questions about these stations, please feel free to ask questions. And Walter, if you have any comments or questions, please help guide us a little bit. Thank you.
Okay, that was a really grand tour. And I think there may be questions about specific stations or how to repair noisy stations. So I'll leave it open for anyone to comment or ask a question.
Okay, thank you, Mr. Muni. I have one question. We have a DDSI site which has a very high short period spectrum up to -70 dB. No installed post hold, but the spectrum is still same when it installed on the surface. Is relocation the only solution, or is there really an instrument problem?
Can you share the result, Mbak Titi?
Which
Okay,
station?
I will try, Mr. Supri.
Oh. Oh, wow. I see. That's an IA station, isn't it? Okay, yeah, that's very high noise. This is located within a city, isn't it? I see. Yeah, that's very high noise. That would be a problem for detecting small magnitude earthquakes and probably even large magnitude earthquakes. Oh, wow, you know how to do this already. You didn't need me. Look at that. That's great.
And after borehole installation, still high noise.
This is a borehole? Wow. That doesn't make much sense at all. That's very high noise.
Berapa meter, Mbak Titi, posolnya?
How deep is the post hole? Do you know? How deep is the post hole?
Yeah, I think not improve the quality of the data. How
Definitely
many
not.
meter, Mbak Titi?
How many meters depth is the post hole?
Yeah. How many meter? Mbak Titi?
Oh, I'm sorry, I muted. Hello, Pak Sobri. I don't know how many, how depth is the postal installation because maybe our friend from Manop Management Operasi or big earthquake center can answer it.
Yeah. I hope that the problem is not in the technician.
Yeah, I don't know what the problem is about instrument problem or
Wow.
higher cultural noise.
Yeah.
It doesn't look any different, does it? Doesn't.
Yeah.
Boy, that's hard to say. Is it the same sensor or is it a different sensor?
Yeah.
I think is it the same sensor?
Yeah, I think you try two different sensor first, Mbak Titi, to make sure that the
Wow.
instrument is okay.
I've never seen high noise like that. That's incredible. There must be something that's some very high noise level source. Is there a
Yeah.
generator or a diesel generator sitting very close to the station?
Yeah.
That's it.
Yeah, and also might be because of the bad cable connector, Mbak Titi.
Maybe I don't know until now, Mr.
Mhm.
And the seismic signal is also bad, I think.
Yes. Is that the diesel generator going on every?
Ini dekat apa, Mbak? Dekat
Dekat
warteg.
ini tangki memang
Kilang minyak mungkin.
Iya, kilang minyak, Pak. This is near oil refinery and center of human activity, Mr.
Okay. Yes, that's very noisy. That's incredible. How close is the generator? Is it
And
just a
so,
few meters?
what is the solution? Can we the solution can we should do to enhance the performance, Mr.
Oh boy. I would say drill a very deep borehole or just remove it. Put a strong motion sensor there and maybe not try to use a weak motion because that's so noisy. Remember that Brune source spectra modeling lines that I showed earlier? I don't think you'd be able to detect a magnitude 5 with that. Very close. So that's, yeah, I would say maybe not a good location for a weak motion sensor. Is this an STS2 or is it a nanometrics post hole sensor?
Oh yeah, this is the sensor is I think S type itu trillium horizon and the digitization sensor. Yes.
So it's a nanometrics trillium in a post hole. Okay, that's amazing.
Yeah.
Well, the problem is unlikely to be the instrument. It's definitely the environment.
Yes, exactly.
Iya.
Di daerah mana, Mbak Titi?
Dumai, Pak.
Oh, Dumai.
Iya.
Could that possibly be a train, that line, that road, or? I have seen that type of noise if there's a train that goes by regularly. Could that be a subway or a surface train line?
Maybe, I don't know.
Road maybe.
Road maybe.
Just a
Main
road?
road.
Okay.
Mungkin dekat
Yes.
warung remang-remang kali Mbak. Dangdutan terus.
Ya, mungkin
Just
Pak.
not, maybe not the best location for a weak
Yes.
motion sensor.
Yes, this is apa ya?
You
Daerah
have to
terkembang
relocate.
apa ya?
Relocate to the location.
Yeah, maybe the best solution is relocated. Yeah, Miss. Yeah, yeah, Miss.
Yes, I would say
Saya
so.
siap nemani Mbak.
You could probably use a strong motion sensor there, and if you want to get strong motion recordings, but again, the weak motion, that's a short period channel too, isn't it? It's an SH. I can't quite see it. Yes.
Yes, yes.
Okay, so it's probably not a very quiet sensor either.
Yeah.
Looks like it's a high noise floor. Oh, wow. That's fascinating. That might be one of the noisiest stations I've ever seen. That's quite a, I mean that in a good way. It's fascinating.
Yeah. Yeah, Mr.
Do you have some other examples? Maybe did you find some quiet stations?
Some
Yes.
quiet.
Let's see.
And I have set a PSM. This is we use a trillium complex seismometer and sensor digitizer. We have
Okay.
so many spec here. I don't know why the spec is happen, Mr. Can you explain it? Thank you.
What?
Ini
I'm
lokasi di mana
sorry.
Mbak?
APSM is Agramakmur Bengkulu, Pak.
Bengkulu. Kayaknya agak-agak kampung ya, masih nggak begitu
Iya,
ramai.
apa pemukiman.
Pabrik tahu
mungkin
kali
ya.
Mbak. Dekatnya.
Maybe, Pak.
This looks very similar. High noise at short periods. What were you asking that I explain?
Very spec here, Mr. Spikes.
Like noise,
Oh, very
frequency
Why
noise.
the specs is why the spec happens and what the solution for it?
Wow, good question. Spikes, are those don't look like sensor problems. It's also it just looks like local noise conditions. This is also in a city, I assume?
In the village, maybe. This is.
You have you have
I'm
that
sorry.
satellite image?
I don't-
Okay, so it's fairly well populated there.
Image apa ini sawah itu Pak? Field.
Farm field.
Tuh kerupuk, dekat pabrik kerupuk ya.
Okay. Well, it's also high noise at the short periods, so it's a cultural noise source. I don't know that the spiking is from the sensor or from the local environment. My guess is that it would be the local environment. Can you, again, it looks like a short period sensor, right? So there's not much long period signal there.
Oh ini sumbu akses is frekuensi ya Mbak.
Oh iya,
Yes,
I'm sorry.
in
Iya,
frequency.
this is the access is frequency. I'm sorry.
High frequency
That's okay.
noise.
Iya.
I like. So the highest level is almost at 10 hertz. And those spikes, it's hard to say what those spikes are from. Is it, are there people walking around? Is the sensor located inside of a building, possibly?
Yeah, maybe. I haven't go there.
Because oftentimes those spikes, looks like someone walking by. And
Oh,
so if
yeah.
it's in a building or the basement of a building, you're
Mhm.
going to see a lot of noise. If it is in a building, I would suggest putting it out into the ground, again, digging a post hole. But you really need to get away from these cultural noise sources. If you do it close to a building or a generator or a road, you're going to get very high noise levels like this. This one, I think, again, it just looks like it's inside of a building, possibly, is what I would guess.
Oh, yeah. Okay, Mr. Thank you.
Thank
Okay.
you.
Could I stop share it?
Okay, thank you very much, Mbak Titi.
This is
You're
great work.
welcome.
I'd like to see more of this work you've done.
Yeah, yeah. I'm sorry because of limited time, Daniel. Maybe we can discuss using email to report the result.
Yeah, that would be great.
Yeah, I'm sorry because we limited time here.
Yes.
So we have to finish this training. Maybe
Yes.
Walter, you have any comment?
Well, I'd like to end this 3-day training by emphasizing that the information shared with you is actually very useful and very practical. We are all dependent on good data. Better data will yield better results, quicker earthquake locations, and more accurate tsunami warnings. So I'm very encouraged by the large number of participants and by the progress that you've made. Thank you very much, Dan, for the clarity of your explanations. And I was very pleased by all of the excellent questions. So we will continue the cooperation and maybe have some discussions informally with several regional centers of the BMKG looking at your stations. So my best wishes to everyone. Congratulations on the progress, and the cooperation will continue. So have a good day, and back over to Sulianti or Pa Supri.
Yeah, thank you very much, Mr. Muni, for your great effort in organizing the training. And for McNamara, thank you very much. And we come to the final event of the training. We are going to closing speech delivered by coordinator of Geophysics Research and Development Center, Dr. Supriyanto Hadi. And afterward, we would like to request Mr. Supriyanto to officially close this training. To Dr. Supriyanto, time is yours.
Thank you, Mbak Suli. Honorable Professor Walter Muni, Honorable Dr. Daniel McNamara, thank you very much for your excellent training for the third day. Today is the finishing of the training. We are sorry because Puneli cannot close this training because she have other meeting. As we know that noise is one of the most important problem in our seismic data recording. After this training, we hope that we know what are the main source of the noise. So we hope we know how to install the seismograph in the better way with insulation or post hole or other technique to reducing the noise. Yeah, thank you very much for the Walter and also Daniel. Before we closing this training, I give a reminder to the participant to write training resume material and send to Pak Agung as requirement to get the certificate. Thank you very much for the Walter and also all of the participants. We hope we can improve our collaboration in the future, not just online training, but we hope also visiting the USGS in the future time. We hope. Thank you very much and see you in the next training. Thank you.
Thank you very much.
Yeah, thank you
Very
very much,
enjoyable.
Thank you, Walter.
Thank you.
Yeah, thank you. And we come to the end of the USGS BMKG training on seismic network data quality. We hope that this program can increase the capacity and efficiency of earthquake disaster management, preparedness, and mitigation in the future. Have a nice day. We look forward to seeing you at the next event. Thank
Okay,
you.
thank you.
Thank
See
you.
you,
Thank you very-
Walter. See you.
Thank you, everyone.
Goodbye.
Thank you. Maybe Daniel, can you
Thank you,
send
Mr.
us your email address, Mr. Daniel?
Yes, yes, of course.
Okay. Thank you very much.
Will do. Thank you.
Okay.
Thank you very much.
Goodbye.
Goodbye, everyone.
Goodbye.
Goodbye, Mr. Muni.